Okay, lab 2, we'll do some hands-on exercise on filtration and filter integrity validation methods of different kind. Again, there may be some of you who have done this lab previously. If you have, then like I said before, you can be the leader, so who can help your partner. Okay, so bear with me. Okay, so filtration is very important because it is one of the main sterilization methods during the drug manufacturing process. Think about, main ingredient, the API. Mostly, those are biological molecules, and then many of those biological molecules are very susceptible, prone to damage if we use different kinds of sterilization methods like heat, maybe steam, heat. They will damage the proteins, so you cannot apply that. Strong, maybe light. Again, light energy could be damaging your drug. You cannot use it. And gas, again, if we are dealing with a medical device, yeah, you can use a gas sterilization method, but biological drug, you cannot use gas sterilization method. So then what do you have left with? Mostly it's a filtration only. So by going through the filtration, you remove contaminants that are mostly larger. Okay, so that's why filtration is really important during the biological drug manufacturing, mostly injectable. So if you talk about filtration, there are different types of filters. And so it's a cold method sterilization, which is friendly to the biological drugs, of course. Yeah, depends on the size of the pores found on the filter. There may be macro filters, or you can call them clarifying filters, because those are used as pre-filters to remove large particles of like pollens and aggregates and things like that. So the pore size is about like 10 to 200 micron sizes. And the microfilters have pores small enough that can trap all the living cells, including bacterial cells, yeast cells, and those things. So normally, think about HEPA filter. The pores are small, like 0.2 micron, so you can trap most of the particles as well. So normally it's a 0.2 micron microfilter that's used as a sterile filter. Okay, and then ultra filter has an even smaller pore size, 0.001 to 0.1 micron pore size. So it is efficient to remove viruses. Viruses are much smaller than bacterial cells. Maybe their size maybe 1,000th or smaller. So they would go through microfilters, but they can be trapped on the ultra filter if you use it. So it's used as a viral filtration. And the nanofilter, like reverse osmosis, when you do OFI filter filtration method, reverse osmosis, we talked about it, right? They use nanofilters. So even very small organic compounds and ions can be removed. So since filtration is used a lot during the pharmaceutical manufacturing, of course, the FDA has a lot to say about those. Okay, so manufacturers should, using filtration in parenteral injectable drug manufacturing, should demonstrate the following. What are the followings? Scientific documentation of the levels and effects of the biobuttons in pre-filtered material. Okay, and then the sterile conditions of the filter itself, its housing, and associated tubing have been scientifically qualified and by the manufacturer. Okay, it's not the vendor who's selling those, it's the manufacturer of the drug who has the responsibility of the quality and the condition of those you're using. Okay, and the validation studies demonstrating the combination of filter product and processing condition resulting in sterile filtrate. Okay, so you have to have the study done, and study results should be documented, saying that indeed this filtration method is efficient in removing contaminants, and then your drug is not sticking with the filter. You're not losing your drug during the filtration. So all these should be studied and then documented. That's what the FDA says. And if you look at the filter design, there are different types of filters that have different shape and structures. Flat filters, so they have stacked disc filter, such as millipore, millipack system. We're talking about this. Okay, flat filter. This is the filter disc. You just see that it's housing. Okay, and then cylinders or cartridge filters. Okay, so inside of cylinder like this, there are pleated membrane, filter membrane you can see in there. So the reason for the pleating is by pleating you can have more surface for the filter. So more things will be filtered through the filter surface. So Kuno, Messner, Millipore, Pal, Sartorius, these are vendors who are selling these cylinder cartridges, filter cartridges. And capsule filter types, cartridge encapsulated in a rigid shell made with polycarbonate or polyethylene material. So we're talking about these guys. Okay? So filters can come in different structure and shape. Then how do you validate your filters before you use? So like I said, the FDA says what? It's your responsibility to validate and demonstrate the efficiency. Okay? So you have to do your testing and document the result of the testing. So in terms of validation method, there are two kinds of validation method. One is considered as destructive testing. So what it means is when you do your testing, your filter should be sacrificed, and because testing itself is kind of destructive to the filter itself. So you have to use a filter for your testing, and that's it. Okay. So there are three main tests that are performed, and you consider those as destructive testing. One is bacterial retention test. Okay, so you will use real bacterial cells of chosen species. You mix them up and you do the filtration and prove that yes, indeed the bacteria will be filtered, retained by the filter. Okay, so once you are using the living bacterial cells, of course that filter should not be used for your drug product manufacturing. That's why it's destructive. And the filter extractable and leachable test. So filter is made out of some material, maybe plastic or chemicals, whatever, and you need to make sure that there's no extractable or leachables that's coming out of your filter itself or filter housing. If they come out, where would they go? They may end up being mixed up with your drug, and you don't want that. You want those chemicals going into your drug, right? So you have to do the testing to make sure that none of these is coming out and mixed up with your drug. Okay? And the compatibility test of filter with drug product. So again, if your drug product is binding on the filter, it doesn't come up after filtration, then you're losing expense of your API. So you don't want that, right? So you have to do testing to make sure that your drug is not binding to the filter itself. So these three tests are considered as destructive testing. So you do the testing and document it, and that'll be it. Okay, so these testing are done before your manufacturing, before your adoption of the filter for your manufacturing. Okay, and then there's a non-destructive testing. These tests are done before your filter use and after your filter use. So after this testing is done, that filter, after passing this test, can be used for your manufacturing. And then after the use of the manufacturing, that filter will be going through this testing again to make sure that there's a damage occur during your manufacturing process. Okay, so these three non-destructive testing that are combined with your manufacturing process. So bubble point test, okay, normally used for small filters, and then forward flow testing, normally used for large filters, and pressure hold testing, again used for the large filters. These are kind of non-damaging friendly testing method that are quick and easy, so you can do that before your filtration, and after your filtration you do that again. Okay, so understand difference between destructive versus non-destructive testing. So out of those testing, you will do a hands-on exercise on bubble point test. So bubble point, what does that mean? You will do this testing on your filter, especially small filters, and normally you will shoot out a gas to the filter that is wet with some kind of solvent. Okay, so the filter will hold the pressure, the gas pressure going through its surface tension and everything. Okay, so there are certain pressure it can hold, and eventually the gas will go through your filter. Okay, at certain pressure point. So then the gas that's coming through your filter will form some stream of bubbles. So at that bubble point, you'll check the pressure of the gas that is penetrating your filter. So that is the bubble point test. That's what it is exactly. So the manufacturer knows what the bubble point pressure is for each filter they manufacture, because they did a pre-test. So it's like this. Okay, so here's a pressure gauge, and then there's a filter, small filter that you can test. Okay, there's a filter again, and then there's a tubing coming out of that filter, and then the tubing is located on some kind of solvent. Maybe it's a water, or maybe it's a methanol or something. Okay, and you are shooting air through, pressurized air through your filter. Okay, if it's an intact filter, it'll resist until a certain pressure point. Okay, but if it's a damaged filter, there will be much less resistance. So the bubble point, where the gas is going through a filter and coming out on the other side as a streamer bubble, okay, if it's an intact filter, it'll hold up to a certain pressure point, like 70, 50, whatever. Okay, but if it's a damaged filter, that pressure point will be much lower. It'll be maybe 10 or 5 instead of 70 or 50. Okay, so that's how it works. Okay, straightforward, very simple, right? So in the lab, you will be able to find these filters. Those are called TPFE filters. Okay, those are hydrophobic filters used as a kind of gas filters for your bioreactor. So I don't remember what that TPFE stands for, but you can look it up if you want to. And so that's made by a company called PAL. So they have the pore size of 0.2 micron, kind of stereo filter. That's why I use. And the PAL says the pressure point is 16 psi per square inch. Okay, so you'll do the bubble point test using. So that's an inlet. You're going to connect a couple of tubings there, inlet and outlet. Inlet will be connected with the gas tank. You will turn on the gas tank, and the pressurized air will go through. Outlet tubing will be connected, and it'll be located in the inside of a beaker that has methanol. So you'll observe the bubble stream coming out of the outlet tubing while looking at the pressure point. Okay, so that's how it should work. So if it's undamaged intact filter, the bubble point will be about 16 psi. You'll observe if you can find it, and that's how you validate your disc filter. So you'll be given with 3 disc filter type, maybe red tape the filter, blue tape the filter, green tape the filter, and validate them, all of them, by doing the bubble point test. Okay, so if the bubble point you observe is 16 psi or above, the filter is passed. If the bubble point is less than 16 psi, your filter failed, so you should throw it away. Okay, that's the first hands-on test. And the second hands-on test is the microfiltration. Again, since microfilters are used as a stereo filtration, we'll be giving you a steady cup filter. So this is the filter design. So there's a filter there that has a pore size of 0.2 micron in there. So you're gonna draw in your liquid that should be filtrated through this membrane. At the bottom is a holding cup, and there should be a vacuum connection. So there'll be a tubing that's connected there. So the vacuum, if you turn on, the vacuum will pull the liquid sitting on the top cup through the membrane, and they'll be dropped to the bottom. So that's how you can pressure liquid that can go through the filtration. So if 0.2 micron filter is good enough to capture all the microbills or not, you can test it. We'll give you a liquid made out of LB. That's a growth medium for bacterial cells. There'll be some bacterial cells in there. So you filtrate it through that and see if the filtrate liquid that has microbills or not, because you want to streak that liquid, filtrate liquid on the petri dish and see if there will be any growth. And you can also streak some of the filter surface and see if you see the captured microbial from there or not. So that's the microfiltration operation, hands-on exercise. That's the second part of the lab. Alright, so very straightforward. It's going to take very little time. Alright, that's it. One important thing is you have to do this aseptically, so you have to operate this under the biosafety hood and aseptic condition. All right.